All right, so the homework solutions should be available, and so the homework was technically due Tuesday, right? So the homework will be available, the solutions, like 5 days from that. That way it's that 20% per day thing, and they should really be released automatically on Canvas. There is another ICA available if you're interested in that. It'll be due before D1, which is Thursday, so a week from today. Their homework C2 doesn't get actually formally assigned until next week, but it is available. Some people have already turned it in. So if you're interested, it's out there. It's 2 questions related to random number generation. They come right out of the chapter. The first question is just sort of plug and chug into a formula. Once you find the right formula, you plug it in, you generate 5 numbers, and you're done. The second question, I give you numbers that could have come from a random number generator, and you used a Kolmogorov-Smirnov test to see if they likely came from a random number generator. And we'll go over the KS test later, but I put a video online that describes how to go through the test. So I actually work an example with different numbers. And so if you're interested in that, I think all the info you need is in the book and online if you want to get started on that C2. Otherwise, just as another reminder, the arena competition is an alternative you can do for your final project. I keep reminding you because I think the submission deadline is like September 30th. If you want to register for that, register a group for that. There's additional competitions. The Flex Sim simulation or competition also, I think, has like a September 30th deadline. 1 sec. And then the Simio one, I don't remember what their deadline is, but I think they actually released the prompt on September 24th. So I think they kind of expect you to be registered before that. Question? Again, unless you contact me ahead of time and we kind of figure out a good reason for it, I'd like to. It's easier for me if you're in the same lab. If you're not in the same lab, I have to do a lot of math to make sure. Because like the worst thing is, like if let's say everybody wants to go to the 8 a.m. lab, and there's just happen to be a lot of people in there. If we get a lot of imports, we might end up introducing so many groups that we won't be able to cover all the presentations. So I need to kind of make sure that whatever lab you're joining, that A, you're able to present in that lab, and then B, that there's enough space in that lab. So talk to me offline about that, or send me an email, and I can kind of try to do the math and figure that out. Other questions? Okay. Yeah, sorry.
On the lab, the second part for the critical path, can we use the Excel function right between, or do you want us to use the B minus A?
I'm okay. If you want to use rand between, that's fine. You don't have to use the inverse transform of rand you want. It was simpler for me to just throw out, like, here's rand and here's like a generic function, and that actually relates a lot to what we're going to be doing later in the class. But rand between, as long as, and I don't remember off the top of my head, as long as rand between gives you a real number and not an integer, then that's fine. As long as you generate an integer between, or a real number between 0 and 1, however you do it, I'm okay with that. And we'll talk a little bit about Lab 3 today, and then, but I have a question.
So for the second part, on the second part of the lab, for the average illustration,
Yes.
that's the average or about?
Yeah, so the question was, on the second part of the lab, I asked you for the average of the total duration. The total duration is the critical path, so I'm basically looking for the average critical path. So I'm looking for one number at the very top, or also reported in your Word doc, that is just what is the average of the max times, where each row has a max time, you're averaging across those. Yeah, and then the bonus is just a histogram of the critical paths. So the critical paths are effectively the total duration of the activity. So everybody's required to get the average. And as a hint, the average should be greater than 9. And then the bonus is to actually generate a histogram of those critical paths to see what that's shaped like. And we'll talk about a little bit later today why the average might be greater than 9, even though all of the individual paths average are 9, and why the shape might be a little funny.
And follow up on this, do you have a concern or care about what
For now, no. I just that's why kind of as a bonus is that I'm going to force you to do a histogram in the homework after this homework when you actually start generating these random variates. But apparently, I'm getting a call. I'm going to force you to generate a histogram, of course, from an 888 number. So it's complicated. So I have a Google Voice number which rings lots of places, and so hanging up when I have this set up usually means hanging up 3 times. So until it actually goes away. Technology. I'm sorry. What was the question again? I did. Great. I don't. All right. So yeah, histogram. Right. I'm going to force you to do a histogram later, but for now, as long as it's got the right shape, and yeah, of course. I mean, don't do 2 bins. You know, I mean, I wanted to actually capture the shape of it, but we'll talk about later, like how to actually choose a good number of bins. But so for now, just make sure it's shoot for maybe 10 bins. Like that's probably a safe bet for this particular distribution. Any other questions? All right. So last time we've been talking about spreadsheets, how you might call them cell-oriented data flow programming, or their declarative programming language means we only capture relationships between cells, not actually how things are done. And that initially makes them seem like they'd be challenging to implement a discrete event system simulation in, because DES is all about how the state changes, but we can end up representing state. We just have to be kind of clever about how we put all of these representations together. And so our model for that was this simple MM1 queue. So it's a single channel queue. And so we did this example, and this was kind of the bonus on the homework that was due, I guess back on Tuesday, is that, I give you inter-arrival times, I give you service times, and as long as you can capture the relevant relationships between elements within a time and across time, then the spreadsheet can end up populating the whole discrete simulation for you. So some of these are pretty maybe obvious how they work. You start with whatever time, the arrival time, and you keep adding the inter-arrival time, and the cumulative inter-arrival time is the kind of time is the actual arrival time. But other things are a little more complicated, and we went over those formulas last time, like how to calculate the time the service begins and ends and so on. And this isn't how we'll do DES for the rest of the semester, but I wanted you to see that you could do it this way. And that you can end up getting the same answers that you would if you did it the kind of instant by instant, which is kind of up here. And so we just kind of did a quick demo that if I want to know when customer 3 departs, well, the spreadsheet says it departs at 13, and so did the hand simulation. So the spreadsheet can actually end up doing the same calculations that you did here, even though it does them in a very different way. And so that is, were there any questions on how that worked? Or is there anything confusing about? Hopefully this was relatively straightforward. So today I want to grow that a little bit and to show that you can actually make things a little more complicated. You can solve some inventory management problems, and then you can solve Monte Carlo problems like the ones that you do, well, hopefully now at least seen in Lab 3. But then hopefully we can motivate after that, despite the power of these spreadsheets. In the end, if we really want to do interesting things, we probably need more special purpose tools, because these start getting very cumbersome once we go beyond something like these simple Monte Carlo sims. But when we get through we've got to walk before we can run, and so let's walk through these spreadsheets. So this is kind of the model I'll start with here. So if you're not familiar with this notation, this is basically saying I've exponentially distributed inter-arrival times coming in to 2 servers, and there's some dispatching policy as to who goes to what server when they're busy. And each server itself has an exponentially distributed service time. So that's, the big focus here is now we have 2 servers instead of 1. And the dispatching policy we'll just use is go to Able, go to the top one. Unless it's busy, then go to Able. And so that's what we want to try to simulate using a simple spreadsheet. And so this is example 2.6 from the lecture text. And so we start out just like we started before. So we've got callers coming in because we've got one arrival process. So we've got one set of inter-arrival times. So for now, I'm giving you all of those. But already you now know after the lab that you can draw random numbers from Excel. With a little bit of arithmetic, you can take a uniformly distributed random number from 0 to 1 and turn it into a uniformly distributed random number between anything and anything else. Now, with a little bit more arithmetic, you can take that same uniformly distributed random number between 0 and 1 and turn it into an exponentially distributed random number. So even though Excel may not have a function that allows you to draw from an exponential distribution, we will learn in this class how you turn a UO1, so the uniformly distributed random number between 0 and 1 that you do know how to draw, into pretty much any distribution you want. So we haven't learned that yet, so I'm just giving you these times, and I just picked them as integers to be easy. But eventually, you can imagine populating these cells with draws from random, and then every time you resave the spreadsheet, you actually would get different things here. So you would get you got a certain set of arrivals that would be like, simulating one day, and if you resave the spreadsheet, it might redraw all these numbers, and it's like suddenly you're simulating another muffin schedule. And so that's where we're going. We haven't figured out how to do that yet. That's why I'm just giving you these lists of numbers. But in reality, we very rarely do get lists of numbers unless you're taking them from real-world data. Then we also have this list of numbers, these service times, and likewise, you could have Excel draw these randomly if you knew how to make Excel draw from an exponential distribution. We haven't figured out how to do that yet, but that's just a couple lectures away. All right, so if we have all of these, then, calculating arrival time. Well, that's the same way we did before. We just accumulate all the inter-arrival times, and then we end up getting this arrival time distribution. So it's just whatever the previous one was plus the next one gives us the next arrival. Then, now we have to be a little clever here in dealing with this dispatching policy. So again, I have to try to think of a relationship that holds across time and space for every line of this spreadsheet. And so what I'm going to do is write a little bit of Excel using an if statement in Excel that basically says, well, if I look at my columns here, I have got a column when Abel is available and when Baker is available. So, basically, if right now I'm saying these are how many are in the server right now. So currently nobody's in Abel or Baker. So right now, both are available. So if I can say here that, if Abel is available, regardless of what Baker is, go to Abel. Otherwise, if Abel's not available, go to Baker. And that's basically what this will end up being here. It just chooses a server based on who is currently busy. And so right now, it arbitrarily chooses Abel, but if Abel was busy, it would have chosen Baker. And all of this looks like it's populated here because I just kind of have a mask over top of a completed spreadsheet. But if you just implemented this, it wouldn't know what to do here until you populated everything else. And so spreadsheets, again, are kind of confusing in that sometimes they don't settle out into something that makes sense until you finish them. So if we move on to the next thing, we say, well, we'll need to figure out when the service begins. And so we've got now, it's a little more complicated version of the single server queue. So we know that the service, if we're lucky, the service begins at the arrival time. So somebody arrives, neither server is busy, or there is a free server available, and so it will just be, the service will begin right when they arrive. So we know that has to be part of it. But it's if Abel or Baker are not available, there is a column here that is, when they're available. And so this column here says that they're both available at 0, but later on, they might not be available until time 5 or time 6. And so we're going to take the max of when they arrive and the min of whichever server is available. So if Abel is available first, then that will fill in this column. And if that is after this arrival time, then we have to wait for Abel. So that's where this formula will come from. And so again, this ends up populating out, but it wouldn't, if you're just writing this line by column by column. So then you have to say, well, when does each server complete? Well, we know that able, so if we say able's completion time is going to be if able is the chosen one for this customer. So for customer 3, if able is the one that's chosen, then we know that we just take the time that service begins and we add the service time for customer 3. And that's what gives us when able is going to be complete. Otherwise, if it was Baker that was chosen, then we totally ignore this row and we just say, well, the completion time is still the same. So initially, able was chosen up here. And so we know that service began at 0. We add 4 to it, so able will be available at 4. That means the next customer who comes in will not pick able, they'll pick Baker. And so able's next completion time will just carry right on through. And then we do something similar with Baker, where it's the symmetric case. We just flip it so that it just sort of only pays attention when Baker is selected. And so that actually ends up doing everything for us, because now that once we have when the service times are complete, then we can figure out all the rest of this stuff. So we now know that, so if we go back to when server available, the way that formula came in, which, right here. So this when server available here, that's just going to take the previous completion time. So if I were to look across here, caller 4, able, it says able will be available at 7. Well, that's just in the previous row, that's able's previous completion time. So once we know all the completion times, we know all the availability. Once we know the availability, we know which one will get chosen for each customer. And once we know that, everything else falls out. So this, in principle, gives us a way to use a spreadsheet to go through an MM2, a simulation of an MM2 queue. So you could generate all sorts of arrival to inter-arrival times and all sorts of service times, and it would just recalculate. And then we can calculate these performance metrics here, like how long did this caller have to wait? Well, that's going to be whenever their service time began minus their arrival time in 1 second. And then how long did they stay in the system? Well, that gets a little complicated. If able was chosen, it's able's next completion time minus arrival, or if Baker, it's Baker's next completion time minus arrival, and that gives us our total time in system. So these are kind of, somehow our state variables are tied up in here, and our performance measures are tied up in here. And so in principle, we can do this giant simulation just by setting up these rows and keep filling down, and then we don't have to do any sort of hand simulation. Question?
Yeah, so over there basically just indicates two servers, right?
The 2 here, yeah, that just means that there's 2 servers. So there's a single channel feeding it in, and it then splits off into 2 servers. And both servers, the M's we'll go into later, the M basically means that it's an exponential service time and an exponential inter-arrival time.
Is it always going to be just one channel server?
No, but this is just kind of so if you'd probably be introduced to this notation, Kindle's notation in 470, when you start talking about networks of queues and things like that. And so these are kind of the building blocks of much more complicated networks. And so the simplest networks are the ones where you've got sort of one that's feeding in, and then you've got a certain number of servers. But then you'd imagine you could build those up into other things. And so we're just starting with the simple ones just to show that, at least for the simplest ones, the logic exists that you could implement this in a spreadsheet. But kind of the punchline here is, although this is possible, this is already getting a little bit crazy to sort of keep track of. All this conditional stuff, like you write, there's a lot of stuff that could go wrong. And this is very, very simple to implement in Arena, much, much simpler than what we do here. So even though we can do it here, and it's totally valid, as we get to more and more complicated cases, this is just not the way that you want to go if you want to quickly be able to simulate complicated systems. So I'm not going to ask you to ever simulate an MM2. I'm just trying to hopefully justify to you that it's possible that this could be done. But there are reasons why you wouldn't do it this way, because it would just, already, it's just, all these conditionals and everything, it's a pain. Imagine if you had 3, 4, 5. Or even worse, imagine if your boss said, well, what if you already did this nice simulation of 2? What happens if we added 3 servers? What if we went up to 3? Imagine all of these cells you have to go back and change these conditionals so that now they apply to 3, Abel, Baker, and Charlie. So it would be a mess. So that's kind of why we have these tools like that. All right, any other questions about how this is implemented here? Again, I'm not going to, the MM1, I'd like you to sort of feel like you could do that on your own. The MM2, I'm okay with you kind of coming away with it saying, you know what, if I had to figure this out, I could, but I don't necessarily know how to do this on my own. I'm not going to ask you in a homework to do an MM2, but maybe on a midterm, I would ask you to be able to interpret or fill in the gaps on the MM1. All right, so but let's see a little more interesting examples now. So inventory management problems are kind of, again, one of these classical problems in operations research. And they're a little different than these queuing problems because we usually assume that the inventory checking period is known ahead of time. It's deterministic. So the idea is every day, every hour, every minute, you check your inventory, and then you take some action. Now, the randomness comes into play is that you may not know what the demand is. How much demand do we need to meet with this inventory? You also may not know how long it's going to take when you make another order. So you order something, and it might take, it might take a day for that shipment to arrive 1 week, but the next week you do an order, and it maybe takes a whole 6 days for that shipment to arrive. How do we deal with that randomness? So that's where we kind of the randomness is introduced, as opposed to the timing of demand orders. We kind of know every day there's going to be some demand. It's the quantity that we don't know ahead of time. So this is much like that muffin baking simulation in Lab 2, where we know that every, whatever I said, every minute or every, whatever the time unit was, we get a random number of muffins that arrive that may or may not go in to the oven. So you can almost think that the empty oven space is your inventory. So you can kind of think, how big of an oven do we need? That's kind of like the inventory management problem here. And the arriving muffins are the demand. So if you have a giant oven, but you only ever get very tiny muffin orders, then in order to fill your whole oven, you might have to wait a huge amount of time to accumulate enough demand before you actually serve that demand. Or you can service it immediately, but then you're going to have a bunch of empty inventory, or a bunch of inventory that you basically bought an oven that you don't use. So that's how this muffin making simulation is sort of meant to model an inventory management problem. But the realistic inventory management, or not say realistic, but the more classic inventory management problems you may have heard about in some of your other classes are like the news vendor problem. So if you're an industrial engineer, you should be familiar with the news vendor problem or the single period or perishable model for inventory management. The idea here is imagine a news vendor. They're selling a newspaper. So every day they go out, they got a bunch of newspapers. And there's fixed prices for those newspapers. We don't know how many people are going to want a newspaper each day. But we do know that at the end of the day, the newspapers have no value. So they're a perishable product. And this is not meant to be only for analyzing, newspaper sales. There's a bunch of other products that approximate this. You can imagine produce would be a similar thing. How many heads of lettuce do we want to stock at the grocery store, given that after a certain period, we're pretty sure that those heads of lettuce are going to be perishable and have zero value. So then they may have some value, maybe you can compost them or whatever, but if we approximate them with this model, it allows us to make decisions about how many heads of lettuce do we order. So that's what we're kind of making. Now the 470 way to do this would be to assume some distribution of demand. So let's say every day you get something normally distributed or whatever, a gamma distributed demand function. So every day you draw a random number from a distribution that you know ahead of time. You might know the mean. And given that you know that distribution, you create an optimization objective like this one, like the average sale price times the minimum of your inventory or your demand. So it's, either you sold your entire inventory or you only sold whatever demand was that day, minus how much it took for you to actually buy each newspaper to stock up. times whatever inventory was kind of left over. So this is sort of the cost you had going into the day, and this is the benefit you had coming out of the day. And so the idea is you want to maximize your profit. So this again is the standard with using those tools from stochastic operations research. You could do some relatively simple math, and you can come up with a demand which maximizes, an inventory which maximizes profit. But the problem with this is that what if we wanted another performance measure? Maybe we didn't care about profit. Maybe we cared about a performance measure that's more complicated than profit. Or what if we wanted to violate some of these key assumptions here? Like, let's say it's not a perishable product. Let's say it has some value. So now at the end of the day, I have a quantity. It's another random quantity because I don't know how many are going to be left over, but they are going to have some value that I can recoup. So that becomes very complicated and perhaps even intractable to solve mathematically. And that's why we might turn to simulation instead. So in the book's case, they say, well, let's make it a little more complicated. We're going to have a quantity queue of newspapers purchased for resale each day. This is how many newspapers you put in your satchel or whatever to sell. And then we've got a demand. And so, of course, if the demand is greater than Q, then we're making too few papers, so we're missing opportunity. If the demand's less than Q, then we're making too many papers, and that's wasted production. And then, so we can then ask the kind of the same problem, the 470 problem here, and we can say, well, how does the quantity Q, how many we buy, affect our profit over 20 days? So already things are getting a little interesting because we can now say over 20 days. It's not something in the limit, or it's not, just we can actually have a time horizon. The other thing is we can actually solve for a distribution and not just an average. So rather than saying what is our average profit, we can actually have a distribution of profit. We can see that there are some universes where we make $200 in profit after 20 days, and there are other universes where we only make $80 in profit after 20 days. Why is this distribution interesting? Well, now, let's say your boss, or let's say you in general, are trying to figure out whether you want to continue to be a news vendor, you might say it's a success if I can make $100 every 20 days. Well, with this distribution, I can now calculate things like, what is my downside risk? What is the probability that I won't make $100 every 20 days? And here, $100, it looks like most of the time I'm above $100. If I just ask up a mean, because I don't know about the variance, it's hard for me to know what my downside risk is. But now that I have the distribution, I can ask these risk questions. How likely is it for, how much of the tail of the distribution meets my criteria or not? So the distribution can be much more interesting and useful, but solving for distributions mathematically can be a lot more difficult, whereas in simulation we kind of get them for free, as I hope you're starting to see as you're doing things like Lab 2 and Lab 3. All right, so the other sort of big inventory, are there any questions about the news vendor problem and turning it into a simulation? So, of course, we don't know exactly how to do this yet, and if you go to the book problem, they actually do the news vendor problem in a spreadsheet. So it is possible to get this output from a spreadsheet. So this is one of the classes of problems that is still relatively simple. If you want to get a little more complicated, again, this would be even easier to build in Arena, as you'll see later. All right, so another sort of classic inventory management problem that we can do in SIM, and we frequently investigate in SIM, are these order up to problems. So an order up to MN problem here is this thing where I've got, I review my inventory at certain periods here. So that's this N. It's the length of time until my next inventory review. And then at the review, I order some quantity that brings me back up to a particular level. So there's two decision variables that we worry about when we do the operations research here. How frequently do I check my inventory, and what level do I then bring things back up to? And so the force that's fighting against this is, of course, the demand, which is random, and the lead time. So someone's going to come and they're going to buy a lot of my inventory. So that's, this reduction in inventory. But then when I order up to, the lead time, so how long it takes for my inventory to then come back up, may also be, there may be some delay there. So even though, I might think that, well, based on the demand distribution, as long as I can order up to here on this day, if it actually takes a long time for that order to arrive back for me to restock my inventory, I might actually want to check my inventory earlier and order up to earlier so that I account for this delay in the demand. So this becomes a more complicated, it seems simple, I just need two variables. How often do I check and what's my regulated inventory level? But it's complicated to figure out how do we come up with these numbers. And so we can do that in Sim. And so in the book version, they set up a little spreadsheet where every M days they order enough refrigerators to bring the inventory up to M units. Orders take several days to arrive, and that several days is a random variable. So it's, and here, I don't know if they actually draw from a random number variable or if they just give you a list of numbers, but where we're going, we would just draw that from a random distribution. And then each day there is a random demand which reduces that inventory. And so then we can then ask performance questions. So we can say, how does the MN ordering policy affect, say, how many back orders we have, how often things go into the negative or lost sales. And then this spreadsheet can give us kind of a solution to that. So this is another type of problem that we can actually answer in a spreadsheet or that we can answer eventually in Arena. So there will be a lab where you'll effectively build an order up to system in Arena. And we see that it's a relatively simple pipeline where we can ask a lot more complicated things. So, again, these are standard inventory problems you should know as an IE at this stage in your career. Any questions about this? Okay. So, all right. Now, trailing off here, so that getting into Lab 3, you're starting to work with Monte Carlo simulations. The first part of Lab 3, you just estimate pi using a kind of a standard method. I go into, in the lab video, I go into the definitions of like where this term comes from. It was actually a code word used to describe this technique, which they used to analyze the physics behind nuclear weapons, but they couldn't discuss it using this technique out in the open, and so they came up with this code word, Monte Carlo, which has to do with the casino in Monaco, the Monte Carlo casino, and that was their way of inferring, this new randomness technique. And coming out of this came all sorts of new random number generators, all sorts of things that are used on all sorts of modern computers today. But it's kind of interesting that it all came out of these physicists and mathematicians trying to wrap their heads around nuclear weapons. And now we use them to estimate pi and come up with better inventory distributions and so on. So the types of problems you can solve with these, the first problem in the book they go into is these reliability problems. I think this is a really interesting problem. So you've got a machine with 3 ball bearings, and this, again, could be modeled. We have the same sort of problem where a building has got 100 fluorescent lights, and you want to decide when to replace those fluorescent lights. Every time you replace a ball bearing, you have to pay for that ball bearing. But you also have to take the machine down, and you have to pay for the person who actually does the replacement. So there's all these different ways that you can pay this cost. But if you don't replace it, there's cost to that as well. So like in a light bulb, the building can keep running until there's a certain amount of redundancy. But eventually, once the room is totally dark, it's inoperable. But a machine like this, of course, if the ball bearing fails, then the machine goes down. And so we can't tolerate any more than one failure. One failure is all we can tolerate. So we have to actually replace them a little early. And so the question is, when do we replace them? And do we replace all of them? So imagine 3 different policies. Whenever one ball bearing fails, wait for it to fail and then replace only that one. Or when one of them fails, you could replace all of them because you sort of anticipate the others are going to fail sometime soon. Or you could just replace all 3 of them on a regular schedule, even if they didn't fail. Now, these two seem like you're wasting life in those ball bearings. But if you consider that there's the downtime that you accumulate while you're doing the repairs and the labor is just as costly, then it may actually be better to then waste a little bit of the ball bearing because you end up benefiting in less downtime and less labor. And so that's kind of the complicated question that we would like to solve with this experiment. And so our hypothesis here is that accumulated downtime and labor costs are greater than gains from operating ball bearings for the full lifetime. And so if we run a simulation, then we should be able to see that if all ball bearings are replaced at the same time, then the total accumulated cost will be less than the case where each ball bearing is replaced as it fails. That's what we're trying to test. We don't know if this is the case, but that's why we run the simulation. So we run a bunch of replications under one condition, a bunch of replications under the other condition, and compare the average costs using a statistically valid method like a t-test, and then that tells us which policy is best. And so you can imagine implementing this, every row having a lifetime of failure times for each ball bearing, and then each sample is a lifetime and a delay accumulated from 15 rows. And so the simulation runs for 15 rows. So each row are 3 ball bearings, and then you can imagine that those 3 ball bearings, just like the numbers that you're using in your critical paths for lab 3, so you might say that, well, when one fails, we have to replace all of them. That's just like your critical path, where one path determines everything. Or you might say we wait for all the others to fail. So that kind of depends, that changes the way in which each row relates to each other row. And then we can end up deciding, what are the costs that accumulate from these different policies, where this is our kind of experiment. So we're simulating 3 ball bearing lifetimes, which are our 3 random variables. And in each row, we're deciding whether we kind of keep the old lifetime or we draw new lifetimes. And then we end up, every time we draw a new lifetime, we can pay for a new ball bearing. So it's a way in which we can simulate the operation of a machine just by drawing random numbers in a spreadsheet. So if we do that, then we end up getting an answer to sort of these average costs, and we can compare those. Other sort of standard Monte Carlo things are I have a function that is a function of a bunch of random variables. I don't know what the distribution of that function will be after I add all those random variables together. Let's say every bomber carries 10 bombs. Each bomb has a certain distribution of locations it can fall on, and I want to ask, what is the probability or what is the distribution of the total area affected by these 10 bombs? 3 different types?
So, Victoria and Monte Carlo, like in what scenario?
Well, so they're just different types of problems. So these are queuing problems, and so this is a problem where these are problems where your arrivals, the time between arrivals is unknown, but the number of arrivals is known, and the time in which you need to service each one of those arrivals is known. So this is like your standard store clerk problem. An inventory management problem is you know that every fixed time period you have to take an inventory, but you don't know how much inventory you're going to need. And then these Monte Carlo simulations, that's kind of a method in which we are trying to estimate some static quantity, and we do that by running a bunch of random experiments and then taking an aggregate of those random experiments, as opposed to finding some deterministic way to solve a problem. So instead of taking an integral underneath a curve using the Riemann method, there's a way to use a Monte Carlo method to actually sample from a distribution to get that integral. Instead of calculating pi by actually measuring the circumference of a circle and a diameter circle and trying to divide the two, you can estimate pi just by throwing darts in a dart. So I wouldn't pit Monte Carlo against these, but I would say these are 2 types of classic operations research problems, and this is a method you could use that we would contrast with the methods we're about to use in the rest of the class, which are more dynamic. These are more static. All right, so all these Monte Carlo methods are going to look just like your lab 3. You're going to have a bunch of rows, and in each row you're going to draw a bunch of random variables, and somewhere down that row you're going to aggregate those random variables, and then at the end you're going to aggregate across aggregations. And so that's what you did in lab 3.
So basically, a Monte Carlo simulation satisfies what is the probability distribution of something happening.
Usually a Monte Carlo distribution is, you're trying to either estimate an average, you're trying to estimate a distribution, But the key feature of a Monte Carlo simulation is that you're using an ensemble of simple interactions between random variables to try to estimate something else. So I have, each row has got 10 random variables, and I use that to calculate something, and that thing that I calculate becomes a random variable. So then I generate 1,000 rows. So now I have 1,000 random variables that were calculated from 10 random variables per row. And that calculation tells me something useful. In the lab, it might be an estimate of pi, or it might be an estimate of the duration of one of these stochastic activities. So that's, gets to this, I wanted to give this sort of preview of Lab 3 to kind of explain these things. So this Lab 3 comes from section 2.5, section 2.54 actually, of your lecture textbook. And the idea here is you have this full activity that has 3 subparts, which are taken on in parallel. You've got one part that you know will never take less than 6 minutes and will never take more than 12 minutes. And we model it as taking sort of being any time in between with equal density, across that. So it could be, it's just as likely to be between 6 and 7 minutes as it is between 7 and 8 minutes. But it will never take less than 6, and it will never take more than 12. And the average here is 9 minutes. In parallel with that, there are another activity that has 2 sub-activities, one that never takes less than 3, never takes more than 6, so its average is 4.5, followed by another one whose average is 4.5, again, never takes less than 3, more than 6. So the average down this path is also 9. Then you've got this top one where each small sub thing, so these are sequences, you have to do this before you can do this, never will take more than 4, never will take more than 4, never will take more than 4. The average here is going to be 3, 3, and 3, so the average on this top path is going to be 9. So you look at this, and if you were just to ask, so how long until I finish my activity on average? And you might think it's 9. You might say, you know what, it's 3 activities that each take 9 minutes on average to complete. So I'm doing them in parallel. They're not affecting each other. So why wouldn't the whole activity take an average of 9? Does anybody have a thought about that? So take 30 seconds or so and talk to your neighbor and give me your guess as to why the average for the whole activity network might be more than 9. And just try to think it through. It's a puzzle. All right, let's bring it back in. So from the left side of my, stage left side of the room. So does anybody have sort of a thought as to why would we expect the total activity network to have an average greater than 9, even though each sub-activity has an average of 9? Anybody over? All right, cool. Sure, give me your answer. That's right. Yeah. At every individual activity, it's a random number between 2 and 4, 2 and 4, 2 and 4. We know on average it's 3, 3, and 3. So this top one on average is 9. This middle one on average adds up to 9. And this bottom one on average adds up to 9. And yet when we have to wait for all 3 of them together to complete before we can say the whole activity is complete, I'm saying the average of the total activity is going to be greater than 9. Yeah. Okay, so I think that's in there. So you're saying that on the first step, so we'll call, you're saying if you have to wait, you're saying that even though I might have gotten lucky enough for these to be 9, this one down here, I might have still had to hang around and wait because there's just some chance it's going to be greater than 9. Right? And that's basically what we're getting at here, is that imagine how you could, in order for you to be 9, that means that some of your realizations have to be less than 9 and some have to be greater than 9. But the total duration is a maximum. That's the function. We're taking the max of these 3 branches. Yeah, question.
So you're basically saying that even though the yard times are randomly distributed, the average is measure of each.
Well, I'd say the average is, I would say that if we're only focused on averages, the average is representative of the top branch, the middle branch, and the bottom branch. But what's interesting is that when you take a maximum of 3 random variables, the average will not be the average of the averages. It's not going to be the maximum of the averages. So that's, I think when a lot of people look at these parallel problems, they think that the expectation of the maximum is equal to the maximum of the expectations. But that's not the case. And the reason that's not the case is that maximum is a funny nonlinear thing where if you think about it, in order for this to be under the average, then this top branch has to be under the average, and this one has to be under the average, and this one has to be under the average. And so now we've got, it's very unlikely, if I happen to be lucky enough to get a fast time out of this one, I probably am not going to be lucky to also get a fast time out of these other 2. And so there is this regularizing component. It's kind of like, let's say you're getting up in the morning and you've got a house full of friends and you all carpool together. And you're excited that you got ready before everybody else and you're ready to go. But you still end up getting to class late because regardless of how fast you were, the speed they take has nothing to do with the speed you take. And so if we're always focused on, it's really hard to get to class early because everyone has to be early. Everyone has to get through their routine quickly. And in this case, it's difficult for us to have a lower than average total activity because that means that every branch would have to be lower than average. And that's just not going to happen very often. But if one of these is above average, it doesn't even matter what the other 2 are. And so that's why we're going to see a shift away from the average so that it'll be greater than average. And so that's why don't expect your duration. When you take your expectations in lab 3, if you got 9 as your expectation, you might have done something wrong. A common error in lab 3 is for people to draw 1 random variable for here and multiply it by 3. Or 1 random variable here and multiply it by 2. You need to draw 3 separate random variables and add them together, and 2 totally different random variables and add them together, and 1 here. So that's one common mistake. If you made that mistake, then some of these things, like the average time being greater than 9, might not hold up. There's other weird things here, like this here is the distribution of outcomes from the lower path. It is not lower than 6, it is not greater than 12, but it is flat in between. Now the top path here is the sum of 3 uniforms, each one of them not less than 2, not greater than 4, but flat between 2 and 4. And yet, when I sum them up together, I got this thing that looks like a bell curve. The bell curve is not less than 6. the bell curve is not more than 12, but it is not flat across here. And that is for the same reason that we just talked about. It's because in order for this to be, basically the idea here is that in order for you to get a 12, then that means that I need to draw a 4, a 4, and a 4. And it's fine. You can draw a 4 from uniform distribution between 0 and between 2 and 4. But to draw 3 of them independently is very unlikely. So although one uniform distribution can give you that maximum value, the sum of 3 of them is probably not going to give you that maximum value very often. So as you start adding things up together, you necessarily take distributions and you squish them down. Does anybody remember the central limit theorem? What is the central limit theorem? Yeah. That's a good summary. Regardless of what distribution you have, as long as you add enough independent draws together, then the distribution of the sum will look approximately normal. And this is the reason why. You're actually experiencing this in the lab. You're adding up 3 of these uniforms and getting something that looks like a bell curve. And basically what you're doing is you're saying, regardless of what the shape was initially, it's very unlikely for me to be on the edges of that shape in everything I'm adding up together. And that's why my mass on the edges shrinks. And that's why I end up getting a bell curve. And so we'll talk more about that next week or the week after that, but that's what you're kind of starting to see here. If we were to plot the histogram through here, it would actually look like a triangle. And so if you add 2 together, it looks like a triangle. You add 3, it starts looking like a hump. If you add 10 of these together, it would look just like a normal distribution. It just happens to be truncated at 6 and 12. All right, so that's kind of what you're going to start playing with. And so in lab 3, in every spreadsheet row, I just want to emphasize you draw 6 independent random variables. So if you want to use rand between, that's fine. Otherwise, use rand and then scale it the way it talks about in the lab by multiplying and adding. But they have to be 6 independent ones. Don't draw 1 random variable and multiply it by 3. You have to add them up together to get this sort of central limit effect. And then the total time is the required max path. And then the distribution is the distribution of those total times, the distribution of those maxes. And in a lot of these things, I've asked how many runs are enough to make these estimates, and it really depends on the variability. So in an experiment like this one, if there wasn't much variability in your output, you would only need 3 or 4 replications. There's a lot of variability. In order to really capture that variability, you might need 500, you might need 5,000, you might need 50,000. That's the reason why we need 10,000 lines for your estimate of pi, but only 500 lines from this, because there's a lot less variability here than there is in the pi estimate. And by the way, rather than dragging down 10,000 lines, if you just scroll down and highlight the 10,000 row, you can go to edit and fill down, and it'll do that. So that's a little, at least on the carpal tunnel, it's a little easier than dragging that tiny little square down 10,000 lines. And there's lots of other ways you can do that too. This is a tip, edit, fill down is easier than drag. All right, any questions about the lab experience? All right, so the only other thing I have for you today is just kind of a message, and that is we can do a lot with spreadsheets. That's all I've tried to motivate here. But if we really want to go into the systems that are interesting to us, the systems that get you a job, those are not going to be the relatively simple systems that we've captured with a spreadsheet. They're going to be far more complicated systems. Systems where somebody will ask you, like at a fast food place, do I use 1 queue with multiple order spots? Or do I use 2 queues, each one of them with an order spot? Oh, and by the way, do I also have people mobile ordering? And how does that fit into that? So at that point, I've got orders coming in from different places, and you're going to be asked to compare not just policies for how to handle these orders, but even whole structures of, do I bother with implementing a mobile order system on an app? Do I bother with building a second line? Which line do I build? A line that looks like this or a line that looks like this? These are problems that are very easy to investigate in Arena but would be a real headache to try to investigate in a spreadsheet. So that's kind of where we're going. So why do we use these simulation tools? They automate tedious coding that can lead into errors. They often include high-level components that reduce the work for you. So in Arena, there's actually carts, conveyor belts, finite length queues that are already done for you. You don't have to build them yourself. And they usually include these graphical options that are a lot nicer to look at than these spreadsheets. And so, so that's what we'll start into. In Lab 4, you're going to see that with an agent-based modeling tool called NetLogo. Some of you have already turned in Lab 4, but if you haven't done that yet, or if you're planning on doing it, that'll be your only introduction to NetLogo in this class, and then we'll do all Arena after that. So that's kind of where we're starting. It'll be agent-based modeling in Lab 4, system, and then process discrete event systems for the rest of the semester. And if you're interested in system dynamics modeling, that's all a whole class on that in 477. All right, any questions? So I'm actually going to give you lecture. So lecture C2 is normally what we do on Tuesday. I'm actually going to skip and do lecture D1, although the ICA that was due is still going to be due on the normal D1 time. And then lecture C2 is just a tutorial that I'll put all online on NetLogo. I have to be away on Thursday, so next Thursday's class will be canceled, and we'll do the D1 lecture on Tuesday. And if you want to do the NetLogo tutorial, you can do that online. Otherwise, let's do the attendance response here. And so the question here is the central limit theorem states that if you add up a bunch of independent variables together, independent random variables together, what is the approximate distribution of outcomes you get? What distribution is the limiting distribution when you add up a bunch of independent random variables?